Somewhere on a server right now, an encryption key is protecting your bank account, your medical records, your identity. Every quantum computing breakthrough brings the day closer when that key can be broken in seconds. This is the story of the breakthrough that just moved that timeline. For decades, quantum computing has lived in a strange kind of limbo. On one hand, it promised to be the most powerful computational tool humanity has ever built, capable of solving problems that would take classical supercomputers longer than the age of the universe. On the other hand, it was fragile in a way that almost nothing else in engineering is fragile. A quantum bit, or qubit, does not behave like the bits inside your laptop. It does not simply sit at 0 or 1. It exists in a delicate superposition, a blend of possibilities that collapses the moment it is disturbed by heat, vibration, stray electromagnetic noise, or even the act of measuring it. That fragility is not a minor inconvenience. It is the single greatest obstacle standing between quantum computing as a laboratory curiosity and quantum computing as a tool that can actually change the world. This is why quantum error correction has quietly become one of the most important problems in modern physics. Not the flashiest, not the one that makes headlines about faster drug discovery or unbreakable codes, but the one that everything else depends on. Without a reliable way to detect and fix errors as they happen, a quantum computer with 1,000 qubits is not more powerful than one with 10. It is simply 1,000 ways for the calculation to go wrong instead of 10. Scaling up without solving error correction does not get you closer to a useful machine. It gets you a bigger pile of noise. To really appreciate how far the field has come, it helps to rewind a little further, back to the earliest theoretical proposals for quantum error correction in the 1990s. At the time, many physicists genuinely doubted whether error correction was even possible in a quantum system at all. Classical error correction, the kind used in every hard drive, every wireless signal, every compact disk, works by making copies of information and comparing them. If one copy disagrees with the others, you know something went wrong and you can fix it. Quantum mechanics seem to forbid this approach outright because of a principle called the no-cloning theorem, which states that it is fundamentally impossible to create an identical copy of an unknown quantum state. For a while, this looked like it might be a dead end for the entire field, a mathematical wall that no amount of clever engineering could get around. The eventual solution, developed independently by several researchers in the mid-1990s, was to spread quantum information across multiple entangled qubits in a way that did not require direct copying at all, but instead allowed errors to be inferred indirectly through exactly the kind of syndrome extraction techniques still used today. That original theoretical insight, once considered a purely mathematical curiosity, is the same basic principle underlying the 800-fold improvement Microsoft and Quantinuum demonstrated 3 decades later. It is a reminder that the breakthroughs making headlines today often trace their roots back to ideas that were once dismissed as too abstract to matter. In the middle of 2026, something happened that pushed this problem forward in a way that the physics community had been anticipating for years, but had not yet seen proven, peer-reviewed, and published in one of the most rigorous scientific journals in the world. Microsoft, working in close partnership with the quantum hardware company Quantinuum, published results in the journal Nature confirming an 800-fold improvement in logical qubit error rates. Let that number sit for a moment. 800 times fewer errors. Not 800% fewer. 800 times fewer on hardware that is available today, using techniques that can, in principle, be extended and scaled. To understand why this matters so much, it helps to understand what a logical qubit actually is, and why it is different from the physical qubits you may have heard about in coverage of quantum chips. A physical qubit is the raw hardware, the actual atom, ion, or superconducting circuit that holds quantum information. Physical qubits are noisy. They make mistakes constantly, sometimes many times per second, because the quantum states they hold are so delicate. A logical qubit, by contrast, is not a single physical object. It is a carefully engineered structure built out of many physical qubits working together and coded in such a way that if one of them makes a mistake, the system can detect that mistake and correct it without ever having to directly look at the fragile quantum state itself. Looking directly at a quantum state destroys it. So instead, engineers use a clever workaround called syndrome extraction. Rather than measuring the qubit itself, they measure indirect properties of the surrounding array, properties that reveal whether something has gone wrong and roughly where, all without collapsing the actual information being protected. It is a bit like being able to tell that a book on a shelf has been damaged by checking the dust patterns around it, rather than opening the book and risking tearing a page just to look inside. This is the foundation of quantum error correction, and it has been a work in progress since the earliest days of the field. What made the Microsoft and Quantinuum result different was not a new theoretical idea, but a demonstration that the theory actually works at a level of precision that had not been previously confirmed and published in a peer-reviewed setting. during a specific type of test called Bell state preparation, a foundational building block used to check whether quantum entanglement is behaving correctly. The logical error rate dropped from roughly 0.8% using the raw physical approach down to about 0.001% using the fully corrected logical approach. That is the 800-fold improvement. In a separate test involving repeated rounds of error correction over time, the improvement was smaller, but still dramatic, with results roughly 51 times better than the uncorrected physical baseline. The fact that these two very different tests both showed major measurable gains is part of what makes scientists confident that this is not a one-off statistical fluke, but a real and repeatable capability. None of this would have been possible without exceptionally precise hardware underneath it. Quantinuum's system, known as H2, uses trapped ions, individual charged atoms, suspended and manipulated with extraordinary control using electromagnetic fields and lasers. Trapped ion systems tend to be slower than some competing approaches, but they buy that slowness with remarkable accuracy. In this case, the 2-qubit gate fidelity, essentially a measure of how reliably two qubits can interact and perform an operation together without error, exceeded 99.9%. That number might sound almost like a footnote, but in quantum computing, it is closer to the whole story. Error correction codes only work if the underlying error rate is below a certain critical threshold. Push the physical hardware's accuracy high enough, and you need fewer redundant physical qubits to protect each logical qubit. Push it high enough, and error correction stops being theoretical scaffolding and starts becoming a genuinely practical tool. That is precisely the threshold this collaboration appears to have crossed with real published evidence. It is worth pausing here to be clear about something. This breakthrough did not solve quantum error correction, and no serious physicist working in the field would describe it that way. What happened is more accurately described as a major validation, a milestone that confirms years of theoretical and experimental work are paying off in a form that can be independently verified and built upon. Quantum computing still faces enormous engineering challenges before it becomes the kind of everyday tool that reshapes industries. But milestones like this one are exactly how those challenges get chipped away, one rigorously tested result at a time. Alongside the Nature publication, Microsoft made another move that signals just how seriously it is taking this moment. The company released an open-source software package called DQ, built into its quantum development kit, specifically designed to support quantum error correction workflows. Most existing open-source quantum tools are focused on building and simulating circuits, the equivalent of writing and testing code before it runs on real hardware. DQ is different. It functions as a hardware-agnostic virtualization layer, meaning it is not tied to one specific type of quantum hardware. Its algorithms for detecting errors, decoding what those errors mean, and mapping physical qubits into logical qubits are designed to accept feedback from multiple kinds of quantum systems, including trapped ion setups like quantinuums, neutral atom systems, and even more experimental topological qubit designs that Microsoft has pursued for years. By open sourcing this tool rather than keeping it locked away as proprietary technology, Microsoft is effectively inviting the rest of the field, competitors included, to build on top of the same foundation. That is a strategic choice as much as a technical one. It suggests a bet that accelerating the entire field's progress on error correction benefits Microsoft more than hoarding a temporary advantage would. This was not an isolated event, either. Earlier in the same year, Microsoft had already unveiled a separate but related advance, a new family of four-dimensional geometric error correction codes, described by the company as suitable for qubits with what is called all-to-all connectivity, a property found in neutral atom systems, ion trap systems, and photonic quantum computers, which use particles of light to carry quantum information. These four-dimensional codes are mathematically fascinating. By essentially rotating the error correction structure through an extra dimension beyond the usual 3 we experience physically, researchers were able to achieve a 5-fold reduction in the number of physical qubits required to build each logical qubit. Fewer physical qubits needed per logical qubit means the same amount of hardware can do more useful work, which is one of the most direct paths toward making quantum computers both more powerful and more affordable to build. These codes also have what is called a single-shot property, meaning they can check for errors quickly in a single measurement pass, rather than requiring multiple rounds of measurement to build confidence that an error has actually occurred. Microsoft reported that, combined, these four-dimensional codes can reduce physical qubit error rates by up to 1,000-fold. 2 major announcements months apart, both converging on the same underlying goal: making error correction efficient enough and reliable enough to actually support large-scale fault-tolerant quantum computing. It would be a mistake, though, to think of this as a story about one company working in isolation. Quantum error correction has become one of the most competitive, closely watched races in modern science, with major players pouring enormous resources into cracking pieces of the same fundamental puzzle from different angles. Google's quantum team, for instance, made waves with its Willow chip, which demonstrated something physicists call below-threshold error correction. In simple terms, this means that as you add more physical qubits to the system, the overall error rate actually goes down instead of up, which is the opposite of what happens in most early-stage quantum hardware, where more qubits usually means more opportunities for things to go wrong. Crossing that threshold, where scale helps rather than hurts, is considered one of the most important psychological and technical turning points in the entire field, because it means the path to bigger, more powerful quantum computers is no longer working against you. IBM has been taking a strikingly different approach to the same underlying challenge. Rather than relying purely on human physicists and mathematicians to design new error correction codes by hand, a process that can take years of painstaking theoretical work, IBM Research has been experimenting with using large language models to search for new codes automatically. Their system, built around a framework called OpenEvolve, generated 465 candidate error correction codes through automated exploration. It is important to note that these candidates have not yet been fully verified for practical use, so this remains an early and unproven approach rather than a finished breakthrough. But it represents a genuinely new direction, one where artificial intelligence is being turned towards solving one of the hardest problems in the field that, in a sense, made modern artificial intelligence possible in the first place. There is something almost poetic about that. The tools built from decades of computer science progress are now being pointed back at the frontier of quantum physics, in the hope of accelerating it the same way they have accelerated so much else. Other companies are chasing their own angles as well. Quera has focused on what are called magic states, a specialized resource that certain types of quantum algorithms require in order to perform tasks that ordinary quantum operations cannot achieve on their own. Alice and Bob, a company built around a different philosophy of qubit design, has pursued what are sometimes called cat qubits, engineered specifically to be naturally resistant to certain categories of error before correction even begins, essentially trying to build hardware where fewer errors need to be fixed in the first place. IonQ, Quantinuum's competitors and collaborators alike, Nord Quantique, Inflection, and Rigetti have all announced their own error correction advances over the same period. This is not a field with a single leader coasting toward an inevitable finish line. It is a genuine multi-front race, with different companies making different bets about which physical platform, which mathematical approach, and which engineering philosophy will ultimately scale best. Academic institutions remain deeply embedded in this race as well, not as bystanders, but as active contributors, shaping the theoretical foundations that companies then race to implement. Researchers from the Korea Institute of Science and Technology, the University of Chicago, and Seoul National University collaborated on a fault-tolerant quantum computing architecture that combines two very different types of qubits, discrete variable qubits and continuous variable qubits, into a single hybrid error-correcting lattice structure. This kind of hybrid approach reflects a growing recognition in the field that the eventual winning architecture for large-scale quantum computing might not come from a single qubit technology at all, but from clever combinations of multiple approaches, each compensating for the other's weaknesses. Fred Chong, a professor at the University of Chicago, who also serves as chief scientist for quantum software at another quantum company and sits on an advisory board for a quantum hardware startup, offered a description of where the field stands that has stuck with many people watching this space closely. He described the current moment as being comfortably inside what he called the era of escape velocity, explaining that quantum devices have become good enough and error correction codes have improved enough that building a large, genuinely useful quantum computer is no longer primarily a physics problem. It has become an engineering problem. That distinction matters enormously because engineering problems, unlike open scientific questions, tend to progress steadily and predictably once the fundamental science behind them is understood. Physics breakthroughs can stall for years waiting on a theoretical insight. Engineering challenges, by contrast, respond to sustained investment, iteration, and refinement. The same way problems in aerospace, semiconductors, and telecommunications have been solved over the past century. So why should anyone outside a physics laboratory actually care about any of this? The honest answer connects directly back to that encryption key sitting on a server somewhere protecting your bank account, your medical records, and your digital identity. Much of the encryption securing the modern internet relies on mathematical problems that are, for classical computers, essentially impossible to solve in any reasonable amount of time. Factoring extremely large numbers into their prime components is one of the most well-known examples. Classical computers would need longer than the age of the universe to crack strong encryption keys through brute force. But a sufficiently powerful, sufficiently error-corrected quantum computer running an algorithm developed decades ago by the mathematician Peter Shor, could in theory perform that same factoring task in a dramatically shorter time frame. This is not science fiction speculation. It is a well-understood theoretical vulnerability that security researchers, governments, and technology companies have been preparing for years through what is known as post-quantum cryptography, an effort to design new encryption standards that remain secure even against quantum attacks. The catch, and the reason today's encrypted data is not in immediate danger, is that breaking modern encryption with Shor's algorithm requires a quantum computer with an enormous number of stable, reliable, error-corrected logical qubits, far more than any system in existence today can provide. Every advance in error correction, every fold of improvement in reliability, every reduction in the number of physical qubits needed to build one dependable logical qubit moves that theoretical threat closer to becoming a practical one. This is exactly why milestones like the Microsoft and Quantinuum result matter so much to people who think about cybersecurity for a living, even though the breakthrough itself was demonstrated on relatively modest, carefully controlled test circuits rather than anything resembling a full-scale code-breaking machine. It is a signal, a data point, a piece of evidence that the timeline is moving, even if nobody can say with certainty exactly how many years remain before a quantum computer capable of threatening current encryption actually exists. This is also precisely why governments and standards bodies have not been waiting around for that day to arrive before acting. Post-quantum cryptography standards have already been developed and are gradually being rolled out across industries that handle sensitive data, from finance to healthcare to national security. The logic behind moving early is straightforward and a little unsettling once you think it through. Encrypted data that is intercepted and stored today, even if it cannot be decrypted today, could potentially be decrypted years from now once sufficiently powerful quantum computers exist. Security researchers refer to this risk as harvest now, decrypt later. It means the race to upgrade encryption is not just about protecting the future. It is about protecting information that is already flowing across networks and being stored in data centers right now, information that could still be sensitive years down the line, whether that is classified government communications, corporate trade secrets, or deeply personal medical and financial records. Understanding this context transforms how a result like the Microsoft and Quantinuum paper should be read. It is not simply an abstract scientific curiosity confined to physics journals and academic conferences. It is a genuine milestone in a race that has real, tangible stakes for how digital security will need to evolve over the coming years. An 800-fold reduction in logical error rates does not immediately put anyone's encrypted data at risk, but it is a meaningful, independently verified step along a path that ends eventually with quantum computers powerful enough to matter far beyond the laboratory. And when you consider that this improvement was paired with an open-source software release designed to let other researchers and companies build directly on top of the same techniques, the potential for the pace of progress to accelerate further becomes even more apparent. There is also a broader lesson buried inside this story, one that extends beyond quantum computing itself. Genuine scientific and engineering progress rarely arrives as a single, dramatic, headline-grabbing announcement that instantly changes everything overnight. It tends to arrive the way this breakthrough did, as a steady accumulation of rigorously tested, independently verified, peer-reviewed results, each one building on the last, each one closing a little more of the gap between theoretical possibility and practical reality. The 800-fold improvement demonstrated by Microsoft and Quantinuum did not appear out of nowhere. It was first announced back in 2024, and it took roughly 2 years of additional scrutiny, replication, and peer review before it was confirmed and published in one of the most respected scientific journals in the world. That timeline matters. It is a reminder that the difference between a promising early result and a trustworthy scientific milestone is often measured in years of careful, unglamorous verification work, the kind of work that rarely makes headlines on its own, but is exactly what allows a field like quantum computing to move from speculative promise toward genuine capability. Looking ahead, the trajectory suggested by all of this activity points toward a quantum computing landscape defined less by a single dramatic breakthrough and more by exactly this kind of compounding progress across multiple companies, multiple hardware platforms, and multiple theoretical approaches, all converging on the same underlying goal of making error correction efficient enough to support large-scale, genuinely useful quantum computation. Trapped ions, neutral atoms, superconducting circuits, photonics, and topological qubits are all still very much in contention, each with its own advantages and its own unresolved engineering challenges. Nobody in the field is claiming to know with certainty which platform or which combination of platforms will ultimately dominate. What has changed, and what results like this one demonstrate with hard, published, peer-reviewed evidence, is that the fundamental question of whether reliable, scalable error correction is achievable at all has moved decisively from open scientific uncertainty toward confirmed engineering reality. The remaining work, immense as it still is now a matter of scaling proven techniques rather than searching for unproven ones. It is also worth thinking about what this means for industries far beyond cybersecurity. Because encryption, while the most immediately visible stake, is far from the only reason this progress matters. Pharmaceutical companies are watching quantum error correction closely because reliable logical qubits are a prerequisite for simulating molecular interactions with a level of accuracy that classical computers simply cannot reach, potentially shortening the path from identifying a promising compound to bringing a new drug to market. Materials, science researchers hope that error-corrected quantum computers will eventually allow them to design new superconductors, more efficient batteries, and more effective catalysts by modeling the behavior of atoms and electrons directly, rather than relying on trial and error in a physical laboratory. Financial institutions are exploring quantum algorithms for portfolio optimization and risk modeling, problems that involve searching through an almost unimaginably large number of possible combinations, the kind of task where quantum computers are expected to eventually offer a genuine advantage over classical approaches. Every one of these applications depends on the same underlying requirement: a supply of logical qubits reliable enough to run long, complex calculations without the accumulated noise wiping out the answer before it can even be read. That is precisely why our result focused narrowly on error rates, something that might sound like a dry technical detail to an outside observer, is treated by people inside the field as one of the most consequential developments of the year. None of this progress has happened evenly across the industry either, and understanding the uneven pace helps explain why so many different companies keep showing up in the same conversation. Some organizations have focused almost entirely on hardware, chasing physical qubits with ever higher fidelity, on the theory that better raw materials make everything downstream easier. Others have focused on the mathematics of error correction codes themselves, believing that a sufficiently clever code can compensate for hardware that is merely good rather than exceptional. Still others, like the collaboration between Microsoft and Quantinuum, have focused on the integration layer, the software and control systems that sit between imperfect hardware and the abstract mathematical promise of a fault-tolerant logical qubit. The 800-fold result is notable in part because it demonstrates that this integration approach, marrying strong hardware with sophisticated software and virtualization, can produce results that neither hardware improvements nor code improvements could achieve entirely on their own. It suggests that the eventual path to large-scale, fault-tolerant quantum computing will not come from any single breakthrough in isolation, but from the careful, coordinated combination of better qubits, better codes, and better software working together as a complete system. For now, the encryption protecting your bank account, your medical records, and your digital identity remains secure. But the 800-fold improvement published by Microsoft and Quantinuum in Nature is a clear signal that the foundation for a very different technological future is being laid, piece by carefully verified piece, in laboratories most people will never see, by researchers whose names rarely make headlines, working on a problem whose consequences will eventually reach almost everyone. That is the real story behind the quantum error correction breakthroughs of 2026. Not a single company beating a single university, not a problem magically solved overnight, but a genuine, hard-won, independently verified step forward in one of the most consequential technological races of our time. A race whose outcome will help determine how safe your most sensitive information remains in the decades ahead.